Good afternoon, everyone, and welcome to this month's Engage session featuring the Goddard Science of Artemis. They came up with a very nice title, so I'll read it for you. The Preparing for Science on the Moon Through the Artemis Missions. As we all know, Artemis 1 successfully launched and came back late last fall. So we are preparing for the next Artemis missions, and these four people who sit next to me are part of the team here at Goddard that is supporting the Artemis missions through science. So before we get started, I just want to give a little housekeeping information to each of you. So we will have a live Q&A with the panel members. So for those of you in the audience here, there are microphones on either side of the auditorium. And for those of you who are tuning in virtually, the chat feature has been enabled. So feel free to post your questions there, and we'll get to them at the end of the panel. So first, I would like to introduce our moderator, Noah Petro. He is just announced the project scientist for Artemis 3. Thank you, Noah, for being here. Let's see, we have Kelsey Young, the Artemis Science Flight Operations Lead. Thank you, Kelsey. Dan Moriarty, sorry. Assistant Research Scientist. Thank you, Dan. And Natalie Curran, the Lunar Geologist. So I don't want to take up any more of their time. I want to let you guys hear from them. So Noah, I'm going to turn it over to you.
All right. Well, thank you, Bree. Appreciate the introductions, and thank you all for coming here in person today, and for everybody online. Thank you for joining us. Brianna said it best. Last December, Artemis 1 splashed down. That mission was successful. We immediately turn our eyes to Artemis 2, and on Monday, the crew of Artemis 2 will be announced. And unlike crew announcements for the last 50 years, the crew of Artemis 2 is going to go fly by the moon. It hasn't been done since Apollo 17 in December 1972. As we've said now time and time again over the last several months, Artemis is happening. We're actually going to send humans to the moon. That question should no longer be asked. It's a question of timing, but it's going to happen. And so the folks that are joining me on stage here today are some of the key people enabling that return to the moon by humans with Artemis. We get the question a lot, what is Artemis? Quite simply, Artemis is the next major initiative to send humans to the lunar surface. The Artemis astronauts are set to explore an area around the lunar South Pole, an area that we know is compelling for a myriad of scientific reasons. There's ancient rocks there. There are places that get extended areas of illumination and areas that get no illumination. There are rocks that are some of the oldest rocks that we know in the solar system, as well as things that are interacting with the sun regularly as we speak. So what Artemis astronauts are going to do is go learn about the history of the moon, and by association, the history of the Earth and the history of our solar system. Artemis is also a long-term program. This is not intended to be a program that ends after 6 missions. Artemis intends to be a sustainable set of exploration of the moon, leading towards the development of a long-lived base camp, extended stays on the lunar surface. Apollo famously stayed on the moon for as long as about 3 days. We want to stay for weeks, months, and eventually have a sustained presence at the South Pole of the moon. With Artemis also, we will learn how to live away from Earth. And with that, learn how to live on another planet and eventually help prepare our astronauts and ourselves to go explore Mars. But more immediately, and right now, we're preparing for the first stages of Artemis. Artemis 2 with astronauts will fly by the moon, Artemis 3 with astronauts actually landing on the moon. And the people in front of us here today are helping those missions become a reality. Goddard has a significant role in defining and contributing to the science of Artemis. What will we learn when we go? We're also, of course, playing a vital role in communications, developing technology, supporting the fundamentals of making that mission work. Of course, everyone here at Goddard recalls the significant contributions Goddard made to Apollo in terms of running the communications network. We had a role in analyzing samples, analyzing data that came back from Apollo. And so we're really carrying on the legacy that started over 50 years ago with folks like Paul Lohmann and Jack Tromka in the sciences that made Apollo as scientifically rich as it was. That's enough from me, though. You've come here to hear from our panelists, and so I'd like to take a moment to introduce our panelists. They'll take a second to describe what they do, how they landed here at Goddard, and what they're looking to forward to with Artemis. And so I'd like to introduce my friend and colleague, Natalie Curran, sitting to my left here, who is a world-class geochemist and sample analyst. So Natalie, tell us a little bit about yourself and how you landed here at Goddard.
Yeah, so as Noel said, I'm Natalie Curran. I'm a lunar geologist, so studied geology from across the pond. I've got this weird accent going on. So yeah, I'm from Manchester, UK. So I started out with looking at planetary science at university and did not look back. Once I realized that you could look at moon rocks, I was kind of sold for a job forever, I hope. So yeah, and here at Goddard, I work in the Mid-Atlantic Noble Gas Research Lab, which it's NASA, so we have an acronym. It's MNGRL, but it's better named as Moon Girl, which is very nice considering the work that we do in there. We study lunar samples, so we're looking at a range of Apollo samples, lunar meteorites, and hopefully, at some point, Artemis samples as well.
Excellent. Thank you, Natalie. I'll turn to my right now, and Dan Moriarty. Dan works in Code 698 with all four of us, actually, and so Dan takes a slightly different tact at studying the moon, but almost as critical as understanding the samples is understanding the context that they represent. So Dan, tell us a little bit about what you do.
Sure. So I'm Dan Moriarty, and I'm an assistant research faculty at the University of Maryland here at Goddard through a cooperative agreement. So I look at remote sensing data. So that's mostly data that was acquired by satellites in orbit of the moon. And so as a scientist, what we try to do with that is answer specific questions about features on the moon. So for instance, if you look at a volcano and you're trying to understand how it formed, you might use imagery to look at some of the geologic landforms. You might use topography to measure kind of the volume and the slopes. Use compositional data to understand the composition of the magma and how it may have melted and where it may have came from. Integrating data like that is a powerful way to answer questions. And we answer slightly different questions in support of exploration goals for Artemis. So instead of asking, how did a volcano form, we're asking, where are favorable places to go? Where should we send our surface assets? Where should we land astronauts? Where should we set up camps? So we look at things like topography to figure out where are safe kind of zones without very steep slopes. We look at temperature data to see where might be a comfortable range for them to live. We look at illumination models to figure out where they might have enough light to perform the tasks they're attempting to carry out. And so integrating all this data is what I kind of contribute to the Artemis team.
And Dan, you're being very self-effacing kind of contributor. I think you make significant contributions in that because there are so many different data sets that we're trying to wrangle together, and so getting a handle on the myriad of data sets is no small task. So Dan is one of the leads in trying to understand the full picture of what we have for the moon so that we can go and get those samples for Natalie's lab. But part of going to get those samples is the act of going and getting the people ready to go do that. And so that allows me to introduce our third panelist, Kelsey Young, also in Code 698. Kelsey, can you introduce yourself?
Sure. I'm Kelsey Young. I'm a field geologist by training. I actually grew up here in the DC area, so still got a lot of family here, which is great. Kind of similar to Natalie saying that when she found out that she could study moon rocks for her career, she was hooked. I have a similar story. I went into college wanting to do something that got me outside, got me, understanding the landscape around me. And when I found out that geology was a thing, I was hooked. And then when I found out geology on other planets was a thing, I was extra hooked. So very similar story to Natalie here. So I'm the Artemis Science Flight Operations Lead. So I take basically preparing our astronauts and our flight control teams to support real-time surface operations. So the astronauts are, of course, the tip of the science spear. They're, really critical science team members in helping us accomplish our science objectives. So we need to make sure that they're really well trained and they're able to effectively, execute the traverse plans, the mission plans we put together, and collect the most valuable samples for lab scientists here on Earth to study. It's not just about the samples, of course. It's about the pictures that they'll take, the observations that that they'll make, the science payloads they'll deploy. So it's about getting the astronauts ready to execute our really exciting science plans. But I'm also helping think about how the ground teams will support our astronauts during real-time exploration. So how will mission control be structured? This is something, not in decades have we done EVAs or spacewalks that have been driven toward exploration, right? We have lots of experience doing spacewalks on the International Space Station on an engineered surface, but it's an entirely different ballgame supporting astronauts that are discovering uncharted territory. So we're working on the structure of mission control and the science teams to be able to support that real-time exploration from here on Earth. So that's the role that I'm playing currently for the Artemis program.
So what I hope folks who are following along have picked up on is that effectively there are three, but I'll introduce a fourth main fundamental part of Artemis science. There's the planning component of what do we know about the moon? And I would also point out, just very selfishly, that one of the primary ways that we've learned about the moon is through a spacecraft that's orbiting the moon right now, thanks to that man right there. Francisco Andol's the project, the mission director for LRO. LRO is operated from a room not 50 feet, maybe 200 feet from where we sit right now. And so that foundation of the planning, the data, the understanding of what the moon is, what the moon isn't, is important. There's the implementation, taking the lessons from the data and putting it into something actionable by astronauts so they can go collect samples to go into the third component, which is the study, the analysis. What did we learn from this mission? And so folks like Natalie and labs all across the world will take those samples and say, what did we learn from this? And we can talk a bit about some of the big science questions that we're going to be asking for Artemis. And there's a fourth component that's not really addressed by the four of us, although I'll proxy it for now, is the engagement. We do these things not because we just want to do it ourselves. We want to share that with the whole world. And so for those in the room, you'll see a visualization that's come out of Goddard. And over the last 14 years, Goddard has really led the way for communicating the value of the moon for science and for inspiration as well. I mean, part of the reason I love doing lunar science is not just understanding our nearest neighbor in space, but the moon is beautiful. The moon is captivating. And so in the next couple nights, as we start seeing the crescent moon and start going away from the new moon phase towards another full moon, go out and look at the moon and realize, hot dog, that is 3 days away from us, and we're going to be sending humans, friends of some of us, to go explore that place and learn about our place in the solar system. That's really cool. And so the fourth pillar of engagement is another thing that Goddard, I would say, leads at, is taking the complicated story that we're trying to tell and get that out so that the whole world can come along. Because Artemis is not just about what the four of us want to do. It's about bringing the entire world along in this journey back to the moon. So with that said, I'd like to start talking a little bit about some of the big science questions that we have for Artemis, for lunar science. And so maybe I'd like to start with Dan, if you don't mind. What do you think are the top two science questions that you yourself want to get out of the myriad of samples and observations that we'll get from Artemis?
Yeah, sure. I'll start with one before passing it down the line. So this is a globe showing elevations around the moon. This is the side of the moon that faces Earth as we look up in the night sky. And this map is color-coded by elevation. So blues and greens represent low-lying areas. Reds to yellows to whites are higher elevation areas. And so what you might notice is that this near side of the moon is mostly really low-lying. Whereas the far side of the moon, the side we cannot see from Earth, there are much higher elevations distributed across that entire hemisphere. And so this is what we call the lunar dichotomy. The side of the moon that faces Earth is much, much different than the far side. And that extends across several different factors. So the thickness of the crust, so similar to the Earth, the moon is divided into a core, a mantle, and a crust. So the thickness of the crust on the near side of the moon is much thinner than the thickness of the crust on the far side. Another factor is that the near side has experienced a much higher degree of volcanic activity than the far side. And then the geochemistry of the surface is also much different between the near side and the far side. And this is one of the great outstanding mysteries for the moon. We don't really understand why there are these fundamental differences between the two halves of the moon. Artemis is going to the South Pole, which you'll notice is perfectly situated between the near side and far side of the moon. So we're hoping that some samples we get from the Artemis mission will help us address this kind of fundamental question in lunar evolution. Why are the near side and far sides of the moon so different?
And so, Dan, you know, with those samples, with those observations, surface measurements, we get a lot of information from the rocks. And those rocks go into your lab, Natalie. So when you get samples from Artemis 3 and 4 and 5 and so on and so on, what are some of the science questions, some of the things that you want to learn from those samples?
For sure. So in the MoonGirl lab, one of the main things that we look at is determining the ages of the samples. So whether they're volcanic samples or whether they're some of the first rocks that formed on the surface of the moon, or some of my favorites are the ones that were formed in impact events. So I'll bring my globe out as well, why not? You see some of these large dark patches. Most of that is filled up with basalts, but these were large basins that formed very early on in the moon's history. So we're looking at over 3.5 billion years ago, and trying to, you know, understand when these happened and what type of impact events occurred and what ages they were. Because the moon's so close to us, whatever was happening to the moon is obviously happening here on Earth as well. So understanding when these impact events happened will also help us understand what was going on around the Earth and at the Earth as well. So I'm very interested in, well, for most of our samples were collected so far that we have here on Earth, collected on these near side equatorial region. But as Dan mentioned, we're going on the other side to hopefully South Pole, or SPA, South Pole Aitken Basin, which is one of Dan's favorites, so I won't steal SPA too much. But we're getting samples from there, which we think, and I think Dan's globe will show it better, is one of the largest and oldest basins in the Earth-Moon system. So having an age of that will be really critical for our understanding of the impact bombardment of the inner solar system as well as the Earth-Moon system. So I'm looking forward to that.
Yeah. So, I mean, the part about getting those samples is actually going and getting those samples. And so that gives you an opportunity, Kelsey. In addition to the science that we get out of Artemis, what else are you looking forward to from the entire Artemis endeavor?
Oh my goodness.
Yeah.
Well, I am looking forward to the rocks for sure, for all the reasons that Dan and Natalie said and a whole lot more. I mean, I think inspiration's a big one. Noah, you hit on it earlier. I mean, this is a global journey that we're fortunate enough to be a part of, but I think just inspiring the next generation. I'm somebody who came into this field just being inspired and excited by science and literally looking at rocks. So the fact that we might have an opportunity to do that for the next generation to get them involved in fields like this is, yeah, I think a big driving factor for probably a lot of us.
And because we talked about rocks a little bit recently, Natalie, you brought a myriad of display items, but one in particular that you want to highlight because it's pretty awesome.
It is. So we do, from our wonderful outreach folks here at Goddard, we have a moon rock that you can actually touch. And I'm going to touch it because every time I get an opportunity to touch a moon rock, I will do so. So yeah, this is actually a lunar meteorite that was found in Northwest Africa. And we get a bunch of these across the whole surface of the Earth that have been collected. So some of the Apollo samples got an easy ride back on a rocket. These lunar meteorites, which we find in a lot of hot and cold deserts, actually have to make their own way here. So this is one of them. And yeah, it's really, feel free to come and touch it when you, after this. And for those folks online, I'll do it for you.
So just a general, what can we learn by studying a sample? So the lunar meteorite you have there, it's a rock that came from the moon, we know that much, but what else can we learn about the moon from a meteorite, for instance?
For sure, yeah. So meteorites, unlike, as I mentioned, the Apollo samples come from this near side, the wonderful Apollo samples come from this near side equatorial region. Lunar meteorites come from global representation. We don't actually know where they come from, but they come from a bunch of places. So we can actually learn a little bit more about the rest of the moon. getting an age from a sample like this. So this is what we call a regolith breccia. Now the regolith is the term for unconsolidated material on the surface of the moon. It's all over. It includes rocks and boulders the size of houses, like house rock, or as down to fine-grained soil as well. So you get a mixture. These are my favorite rocks, these breccias, because they're a mixture of rocks. So they can tell us a lot about the different rock types that you get on the surface. So if it's a basalt, what age that basalt will be, if it's what we call one of the crustal rocks, which on the moon, sorry, most widely found rock on the moon is this rock called anorthosite. And I wouldn't say it's rare on the Earth, but it's not too common. But on the moon, every time you look at those bright white areas, all of that is anorthosite. So trying to understand this type of rock and why it's different to what we have here on Earth and things like that, we can learn a lot just from this small sample. We have all these bunch of different rock types. You can learn about volcanism, learn about the early history of the moon, if this got any water in the particles, but yeah.
Actually, you mentioned water.
Yeah.
And one of the reasons we're going to the South Pole is that there are these really unusual environments that are very cold, never receive direct sunlight, and also various remote sensing data sets that we've collected from orbit suggest that there may be water or some version of hydroxyls at or around the South Pole. Now, Dan, you have extensive experience working with one of the key data sets that's helped us understand that there is this peculiar distribution of water everywhere on the moon. Can you tell us a little bit about this volatile story of the South Pole in 20 seconds or less?
Sure. So the moon, in terms of the geometry of the solar system, the moon is not tilted very much with respect to incoming sunlight. And so what that means is that if you're on a high standing area of the South Pole, that sun's coming in almost perpendicular. So high standing areas receive near permanent sunlight, whereas if you're down in a crater or in a low-lying area, there's almost no way that sunlight can kind of get into those low-lying areas. So those areas are in permanent shadow. They're some of the coldest places in the solar system. And so if a water molecule or some other vapor molecule ends up in one of those areas, it gets trapped. It's so cold that that molecule will have so little energy that it cannot escape. And it's stable there over geologic time. So we have billions and billions of years for these molecules to accumulate. There's some evidence from remote sensing data that there's quite a bit of water and other volatile elements and molecules in these cold traps at both the North and South Pole. And so we're kind of excited to see what we'll find when we actually get there.
So part of that excitement is, I think, through the form of surprises, that we know that there are surprises awaiting us. There's a misconception, I think we still hear this today, that Apollo told us everything that we need to know about the moon, which is partially true. It told us a lot about the moon, but not everything. We've come along and learned a lot in the intervening 50 years. And so one of the things I'm looking forward to are the surprises. There are surprising things waiting for us at the moon, surprising insights that we can get from studying lunar samples and exploring the lunar surface. And so maybe to conclude the first portion of our segment here today, before we take questions from the audience and take questions from online, so please put in your questions into the chat box, or what are some things that surprise us about the moon? So I'd like to start at the left and we'll go across the right. So what is something that you find surprising when you think about the moon, study the moon, talk about the moon, Kelsey?
I think maybe one of my favorite phrases about the moon is that it's a witness plate for our entire solar system. I think Natalie said it really well earlier, that everything the moon has experienced, our planet has experienced, but we have really pesky things like plate tectonics and oceans and vegetation and cities and things that obscure the geologic record. They're really great for us, but not so great for the geologic record. But on the moon, we have 4+ billion years of history exposed for us, just as Noah said, a couple days away. And so the idea of going to the moon to learn about the evolution of our own planet is like unendingly fascinating to me. It's definitely a challenge to unpack because of that. we're talking about lunar samples, one thing that kind of blew my mind in grad school is one sample even smaller than that can yield ages from multiple geologic events on the lunar surface. There was one sample I was fortunate enough to work with in graduate school where one 10 millimeter by 10 millimeter section yielded 3 different ages of impact events, just in one tiny section of one tiny sample that the Apollo astronauts brought back. Imagine being a field geologist and trying to interpret that in the field. It's a significant challenge. But if we can unravel that with field work and lab work, we're unraveling secrets not just of the moon, but about how our own planet came to form and evolve and how life evolved on our own planet. So the fact that we can use this other planetary body to understand how we got here is just going to never cease to be fascinating to me.
Sure. Natalie, what about you? What surprises do you think await us?
Surprises? Oof. I mean, the South Pole is just going to be a bundle of surprises of ages, and
I'm going to write that down.
Yeah,
a bundle of surprises.
Bundle of really cool surprises. Nothing that are going to be shying away from. It's I think continuing that, like, I think my favorite thing that I just always tell people is with the Earth-Moon system and some of the pesky tectonics and stuff removed this evidence here, but some of the youngest rocks that we actually get on the moon, so some of those volcanic ones that are maybe 3.2 billion years old, they're 3.5, they're some of the oldest rocks we would get here on Earth, and I just think that's kind of crazy. You always think the Earth has just got all of these answers and stuff, but actually some of the early history of the Earth we can't. It's been removed now, so we actually don't know. So the moon, being the witness plate it is a phenomenal place to go and find something like that.
Absolutely. Dan, what about you? What surprises do you think await, and what surprises you about your continued studies of the moon?
So I think the thing that's most surprising to me about the moon is the diversity of volcanic processes we observed. So on Earth, a lot of the volcanic processes and a lot of the variations in volcanic processes we observe, they're related with they're related to plate tectonics. So they're in areas where you have interactions between continental and oceanic crust. On the moon, it's a one-plate planet, so there are no plate tectonics. We just have one solid lithosphere. But still, there are a huge range of diverse volcanic landforms that we observe. So we see areas of the crust that have been inflated by volcanic material that never quite broke through the surface, but has kind of buckled and fractured the crust, almost like a very hard balloon inflating. We see areas with really steep, high-standing, really silicic magmas, which is a really unusual composition to see on the moon. And again, that's something you'd only expect to see if you have plate tectonics. You have magma rivers, you have vents, you have pyroclastic fire fountains spraying out molten volcanic beads. There's all kind of stuff going on, and I think we don't have there's not a huge amount of volcanic activity at the South Pole itself that we know about, but I'm very interested to find out what do we not know about the volcanic history of the South Pole.
Yeah, I mean, that's why we go, right? We've all just outlined very briefly a number of science questions that beg going to the surface, returning samples, deploying instruments, doing the number of things that planetary scientists do all the time, that Goddard does exceptionally well. I always like to think that at the intersection of the Venn diagram, so I think a lot in terms of Venn diagrams, where do things overlap? That for the types of science that NASA does, planetary science, earth science, heliophysics, astrophysics, if you overlap those 4 circles, the intersection of those 4 circles is the surface of the moon. As Kelsey said, it's a witness plate. You can recreate the entire history of the solar system, events that happened 4.5 billion years ago and events that are happening right now. The interaction of the solar wind with the lunar surface and the lunar environment, and indeed what's happening from the rest of the galaxy and how that's interacting with the surface. The best place in the solar system to do that is at the surface of the moon. And in the next couple years, we're going to have astronauts going to the surface and conducting experiments that help us disentangle all of those things simultaneously. So as part of that journey, we want to open the door to questions from the universe out here. And so, Bree, do you have any questions from online? And we can also, of course, open questions from the audience here.
So if you have questions questions in person, please feel free to go to the microphones. But we do have one question online. This is for Kelsey. Can you tell us how specifically we're training the astronauts for the South Pole?
Oh, can I? Yes, we are training the astronauts to be, well, in a lot of things. The universal we are training them how to launch off the Earth, how to land on the moon, how to launch back off the moon, how to land back on Earth, how to fly multiple spacecraft in between the Earth and the moon and back, how to operate in a spacesuit. But near and dear to our hearts is the science training, of course. And like we said, the astronauts are members of the science team. We are empowering them to address our science objectives. You've heard about some of the science objectives here today. There are many we haven't even touched on. This is a really rich geologic target because of all the reasons Noah just said. There's a lot to train and a lot to do. How we do that is a blend of classroom and field training. So some of the training the Artemis astronauts will get is sitting in a classroom, just like we all do and did here on Earth. Some of it is in the field. We go out to field sites on Earth that look like places we know they're going to see and train them about those relevant rocks in those relevant field environments. We also train them, and this is relevant to science as well, we train them in pressurized spacesuits in NASA facilities. So we have a big pool that we put astronauts in suits in. We have a big harness system that offloads the crew member to to simulate the gravity conditions found on the surface of the moon. And so while those NASA facilities don't have representative rocks, it's really critical for them to get repetitions with the geology tools to do the sampling to get the rocks back to Natalie that she needs in a relevant environment. And so it's this whole picture, right? It's integrating classroom training where we teach them about the fundamentals of impact cratering. It's field training where we take them to impact craters and show them the rocks that they find in impact cratered environments. And then it's bridging that gap of putting them in a pressurized suit in as relevant an environment as we can get to teach them how to put it all together. How do you be in this fidelity environment using tools and getting the right rocks back to us?
So just if I can interject for a moment, you talked a bit about analogs. You're about to go out and go to the field. What are some of the things that when you're out on a lava flow at an impact crater, you're here on Earth. What is it that when you're training astronauts that you're trying to instill in them when they're on a lava flow or on the rim of meteor crater?
Yeah, we do a lot of testing and training in field environments here on Earth. I mean, the one thing is that there's no perfect analog. There's no place on Earth you can go to that is the lunar surface. That would be the lunar surface, right? So it's about putting the entire picture together by allowing those testing and training events to take place in a variety of environments. And so it's really about just how to design those training flows and that testing environment to piece that larger picture together. So for example, astronauts are going to the South Pole, they're going to be looking at impact craters, which we heard are Natalie's favorite. How do we teach them about impact cratering in a classroom environment and then go to the right combination of field environments to train them about lunar impact craters here on Earth? So we have field events coming up this year where we get the astronauts out in field environments, but just as critically, we get all of the mission support personnel in those environments as well, right? It's not just about the astronauts. These human spaceflight missions are massive, massive endeavors that include engineers, they include public communicators, they include the budget staff who make the world go round, the admin staff who make the world go round. They include science teams that are supporting, from science backrooms and from instrument payload backrooms here on Earth. That includes flight controllers, flight directors, capcoms, and all of those people are a part of the mission, and it's vitally important that they all understand these environments as well. And so when we consider the training and testing environment, it's about testing hardware, it's about testing protocols and concepts of operations for exploration in these high fidelity environments to give our team, our entire exploration team, the highest fidelity look at what to expect. I can tell you one of my most gratifying parts of my job the last couple years has been training not just astronauts but flight controllers, engineers, etc., and then being in meetings later after those training events happen and hearing them advocate for science or answer a science question without me ever saying a word. The sneaky convergence happening. And so it's really important to bring not just the astronauts, but the entire team along with us.
Excellent. Well said.
Thank you. So this one is open to anyone on the panel who can answer. So I know here when we build our spacecrafts, when we get them space ready, we put them in clean rooms. There's different versions of different clean rooms. How clean does it actually have to be depending on what they're looking at? So how concerned are you about quotes, Earth stuff contaminating the moon, and what mitigation, sort of how we mitigate that with our spacecrafts, are we going through to not contaminate the moon with Earth stuff?
It's a great question. It's a complicated question because there's an aspirational answer to that, and then there's the realistic answer. The realistic answer is that we've already sent a bunch of Earth stuff to the moon. You know, Apollo was trailblazing in many ways, and one of the things that they had to do was make the whole thing work. They had to be able to get astronauts back to the surface, and one of the things that they did to enable astronauts getting back to the surface is leave things behind, whether it's a rover, a geologic rock hammer, or food wrappers. And so all of that has happened. We can't go back and undo the events of 50 years ago. Looking forward to exploration of the moon, we need to do it, right? We need to land. To do certain measurements, you have to go to the surface. So we want to ensure that we're sending clean material, that we're not contaminating these environments. Now remember, the lunar environment is pretty harsh. You are bathed in radiation from the sun. You're bathed in galactic cosmic rays. You're bathed in heat or in deep cold. You're also getting blasted by micrometeorites over extended periods of time. So, while we can do as much as we can when we bake out an instrument on the Earth, you put it into a vacuum chamber, you heat it up to make sure that as much of the water that you can get out of it, that you kill off all of the microbes, that we do as much as we can to do it. You're still sending something into space. Every spacecraft that goes into space, and John Keller can attest to this, has some water in it. And so, the first measurement that anything that looks for water is going to find water, because there's just water that's inherent in everything that we send from the Earth, which is why lunar samples are so important, because we know they have very, very small amounts of water. So in order to measure those small amounts of water, we need to ensure that we're not sending a bunch of contaminants to the moon. But it is, unfortunately, well, no, it's not. It's inevitable. It's part of the mysteries of science. To make a measurement, you're changing the environment. But we want to mitigate as best as possible that contamination. We are going to these special environments near the South Pole of the moon that can be very cold, that can harbor water, can harbor organics that have been impacted and introduced to the lunar environment through comets and meteorites over billions of years. So it's our job not to only minimize the amount of contamination, but understand the contamination that's happening. And that affords me an opportunity to talk to Dan for a second about understanding contamination, understanding the natural environment as best we can, and what are some of the things that you're doing or thinking about to do that?
Yeah, so we're looking, a lot of the environment at the South Pole kind of relates directly to illumination. So on Earth, we have an atmosphere. That atmosphere helps us redistribute heat. If you have heat coming into the equator, we have cycles in the atmosphere that redistribute that heat all over the Earth. On the moon, there's no atmosphere. So essentially, if you're on the surface of the moon, if you're illuminated by the sun, you're hot. If you're not illuminated by the sun, you're cold. And so I talked a little bit about this earlier, but at the South Pole, the environment is way different than at the equator. So at the equator of the moon, you have essentially 2 weeks of illumination and then 2 weeks of darkness. At the South Pole, you're much less dependent on rotation and you're much more dependent on local topography. So there are some areas that are almost permanently illuminated. There are some areas that are permanently shadowed. And so the environmental conditions, especially associated with thermal conditions, are really just directly tied to illumination. The illumination of the South Pole, again, it's weird. The sun is always going to be very low in the sky. We're never going to have sun overhead like we're used to at the latitudes we live at. So I think that's going to be quite an adjustment for the astronauts to deal with. And maybe, I don't know if Kelsey wants to talk about anything that's gone to prepare astronauts for dealing with some of these weird sun conditions.
It's definitely a challenge. I mean, thinking about that, right? I mean, you either, best case scenario, you have light right in your eyes, essentially, right? But because then at least you have some illumination. Worst case scenario, you're in complete darkness. And so preparing the hardware to be able to support the astronauts in those environments is really critical, but so is testing and training. Making sure that the hardware, that the astronauts know what the hardware can do for them, and also testing the hardware to make sure it does what we think it's going to do. As you might imagine, it involves a lot of late nights because you have to test when it's dark. And so it's also a lot about creating your own sun in those testing environments. And so we've gotten some really creative solutions for testing and training in these field environments to simulate these really critical conditions that Dan is talking about, because this is vitally important to our science objectives on the moon, is operating in these low sun and no sun conditions. And so we have simulated sun, we have sun capabilities, hardware capabilities in the field. We have the suits will have lights on them, of course, so we have the ability to simulate that in the field. We're able to put crew members in darkness and field environments with portable suns and suit lights to be able to simulate those low lighting conditions. We have VR, virtual reality environments, where we're able to really turn the dials effectively based on what time of year they'll be on the lunar surface and at which landing sites. But also, bringing it back to the contamination story, this is something that we care and think a lot about. We want to make sure that the samples we get back, we know what's happened to them, right? So we understand if they're contaminated by something that Noah's talking about, we understand where it came from. We're able to figure this out on the moon before we go to Mars and are potentially looking at signs of life, right? So understanding what the human does to the local environment in a spacesuit that's off-gassing is really, really important. And it's really important for our lunar science objectives to track what happens to each lunar sample. So when Natalie gets it back to her lab, she knows, ooh, you know what? This sample might have been stepped on by a boot before they collected it. And that's important for me to know so I can understand if I'm seeing a signature that doesn't make sense. But it's also important as a proving ground to know that when we go to these high priority, permanently shadowed regions where we know we want to sample volatiles, let's make sure we didn't bring the volatiles in with us. And then when we have astronauts on Mars, let's make sure we understand what that spacesuit's doing to the environment. So when we get a sample back, we know if it came from Mars or if it came from the spacesuit.
And I think one important point about that, to circle back to the question, was we're going to an environment. We want to understand that environment, but it's an opportunity. All of these challenges are opportunities cloaked in uncertainty. And so by going to these environments, leaving experiments behind to measure what have we just introduced as we've explored, by having concurrent orbital observations that are measuring changes in the lunar environment as we go and explore, those are all opportunities. And so as we prepare to send not only missions with crew members to the surface of the moon, but robotic missions, we're going to be doing a lot at the moon. We are, by the very nature of touching the lunar surface, going to be influencing and changing the environment. Well, we'd like to know over what time scales. And so part of that answer to that question is also, well, we need to go and figure out and measure how much change do we impart to the moon when we go explore it. So it's an opportunity to learn how the universe works when you have a meteorite crash into the surface of the moon that introduces some organic material. Well, how much organic material? So let's go find out. And so I think just to circle back and answer, to put a pin on that question, it's a great opportunity. And we do everything we can to understand what we're sending to the surface of the moon, including building two of things so that you know this is the metal we use to build the hammer. And so if we see evidence of that metal on that rock, we know, okay, maybe a little bit of metal spurred off and contaminated the sample with that material. But we'll know those questions and those answers.
Great. Thank you, guys. So we have one question from the audience in person.
What role is artificial intelligence and robotics playing in these missions?
So it's a great question. I mean, let's take the robotics part first. Kelsey, do you want to talk a little bit about robotics, and particularly robotics as it relates to crew exploration?
Yeah, Artemis is more than just crewed missions. It's more than just astronauts on the surface. It involves, commercially landed payload services delivering instruments and payloads to the lunar surface. That includes rovers. NASA has the Viper rover coming up that's going to explore the south pole of the moon to look for volatiles. But we also expect robotic assets to be coming online to support crewed mission phases as well. We expect both unpressurized and pressurized rovers to interact with crew on the surface. But the crew won't be on the surface of the moon for the entire year. So there'll be phases of our future with Artemis that have robotic assets exploring the lunar surface without the crew members in the loop. So there are opportunities for AI, machine learning, autonomous navigation, technology demonstrations with some of these robotic assets. But Artemis really represents a spectrum, and it's far more than just the crewed program. So robotics is absolutely a mission critical part of the lunar exploration program.
And just to bring in the AI component to it, we have two examples of data sets on the table here. Image data altimetry data, laser data, thanks to the LOLA instrument built here at Goddard. That's a huge volume of data that we can mine as humans, as Dan does on a daily basis. But when you ask questions, and I think for many of us, AI is this next cutting edge of understanding exactly how it can benefit our exploration on the moon. So can you trust a computer to go and identify every boulder, or trust a computer and identify every crater or every feature on the surface of the moon? So we are trying to implement some of those tools, not to replace what a human can do, but in parallel with. And so I think our use of AI is still in the very early stages, but we are looking to every resource, every tool to make sure that when we pick a safe landing site, that we are not, as humans, missing something that maybe our automated friends can pick up on. And so we really are trying to throw every possible resource at looking at the surface of the moon before we go send our brave explorers to its surface.
Great, thank you. We have another question.
Okay, so this is actually a great follow-on to the previous two questions, so good timing. We talked a lot about samples and bringing them back to Earth to study. Is there any particular science objective that maybe would be better assessed in situ or closer to the surface, of the moon? Do you have any words to say about that?
Absolutely. I'll let Natalie start, and then maybe Kelsey.
So yeah, I have a few suggestions about this. Age dating, or determining the age of different samples from not just the moon but across the solar system, is very close to my heart. And we have some instruments in development here at Goddard. Shameless plug. It's in our lab that actually could be put on a rover or something like that to actually do in situ age analysis of various samples. So being someone who wants to try and figure out the big question of how many impacts there were throughout the course of lunar history, or not even just lunar but Earth's history and the solar system, I want to sample from every spot on every place of the moon. Can I put that request?
Yeah, put that in.
But that's not always feasible. So having some in situ instruments that can take specific dates of samples as you go, as the astronaut goes, or from different spots on the moon and Mars and broader, asteroids and whatnot, would be super beneficial. And then having those really key samples that we know we need a really precise age on, have them being brought back, because the lab is probably one of the best places to do this. We have super accurate instruments. There's another thing. My instrument weighs about the size of a baby elephant, so I don't think we're going. Can I put that request in as well? Yeah. I'm not sure if that weight is going to reach is going to max out the limit of what we can send. So yeah, in situ instruments are definitely. But yeah, you have a bunch of in situ instruments.
Yeah, I love that question a lot, actually. So you're talking about things that are too voluminous, too high mass to bring back, but there are two other use cases for what you're talking about. One is features that are too delicate to sample without destroying. So Noah mentioned the solar wind interacting with the regolith. We have these things, on the very surface of the lunar regolith called fairy castle structures. I love the name. And these are really delicate features that form from, the very, very surface, interactions between the lunar environment, the solar wind, and the top of the regolith. These are things that are impossible to sample effectively without complete destruction. And so being able to look at those in situ, image them, have astronauts give descriptions before then sampling them, bringing them back, knowing that you're not going to get them back to the lab in the state where you found them. That's just a really impactful way to maximize in situ exploration. And then the other thing is processes that are unsampleable. So the lunar surface, although there are no plate tectonics, there are tectonics. And so we have things called moonquakes that we know occur at various depths beneath the lunar surface. You obviously cannot sample that type of process. You can sample rocks affected by those processes, but you can't actually sample the process. And so having in situ instruments that analyze that type of function, having the astronauts or even a rover or even a lander deploy a seismometer, say, to measure moonquake activity is something that you wouldn't be able to do without setting down, deploying something, and allowing it to do its thing. So there are a lot of reasons beyond just samples to go to the lunar surface. Those are just a couple of them, but Dan, maybe you have another idea.
Yeah, so kind of as Kelsey is getting at, anything you're trying to measure that is a process that's currently ongoing, you kind of need to do in situ, right? So one example would be micrometeorite bombardment. So the moon is constantly being hit by fragments of material over a wide range of sizes, from little motes of dust to small pebbles. We want to get a good understanding of what the flux of those is, how many of those are hitting in a certain area at a certain time, not only for basic scientific reasons, but just to understand safety at the surface. So what are possible modes of degradation of surface assets? If they're being constantly pelted by little pieces of dust or rock, we want to know that, and we want to be able to constrain that to a pretty high level.
Yeah, and I mean, one other component to this that Kelsey has spent a lot of effort on, particularly in the field, is a geologist's best friend in the field are two really clear eyes, right? Look at the rock, describe the rock. But if you can only bring back a subset of the rocks you want now, as a geologist, I hate the idea of how we got to leave rocks behind. But eventually you get to the point of, well, I have this volume of rock right here. These three are all broadly similar. Maybe they have the same age. Maybe they all have the same composition. So we just need one of those. So eventually integrating tools that astronauts can use to help make decisions about what they have collected. Okay, we can only bring back a small volume of rock, that we can't bring everything back. What do we leave behind? And so, the idea that certainly Goddard has led a number of studies into how do you use instruments in the field to help support those sorts of decisions is ongoing. But it is a wonderful opportunity for instrument development to come along for the ride as well. Because it's not eventually going to be just astronauts walking around on the surface. It's astronauts, it's rovers, all working in tandem together. Bree.
Great. So we have another question from in the room.
All right, good afternoon. I guess my question is, there's 13 candidate regions on the solar pole that have multiple candidate sites, landing sites. But hearing your descriptions of what you do and your interests, I guess each one of you has probably a site on mind as to where we should land. Can you share that with us and maybe why?
Absolutely. Let's see. So just to give a little context, NASA last year announced that we have 13 largish regions around the South Pole, many within which are multiple opportunities, places that we can go to land with Artemis 3 in specifically. Now, Artemis 3 will have a real complicated path to get to the moon. They're going to have to land at a place that is illuminated or nearly illuminated, and for 6.5 days, astronauts are going to have to get out and walk. So we can't go land in the middle of the night. We may have to have line of sight communication with the Earth, and so all of these different components will factor into these are the locations that we can go. So when we're ready to launch on December 15th, 2025, or whenever it might be, those are the places that we can go. So we're going to be going through a process of basically down selecting from those 13 regions to a smaller set so that we can go map them, identify the places that we want to go. The 13 regions all have some things in common. They're all near the South Pole. They all are on areas that are have small parts that are illuminated for longer than average, and by definition, they also have areas that are in permanent shadow. None of the four of us will get to pick. This is going to be an engineering. So I would say, for those that have paid attention to the naming scheme of how some of the 13 regions were picked or are identified, some of them have a two-letter name associated with them. Some of them are DM2. Dan, what are your initials?
I don't know, reminds me.
Some have NP next to them. I don't think any of the NPs made it to the last 13, by the way, but that's okay. And so we all had a small role in saying, hey, these are interesting places to go. Not just interesting because, oh, they're on the moon, but there are science questions that we want to address there. So I'll preface this by saying, when we say, hey, this is an area that I find interesting, there's no thumb on the scale for this. I'll start by saying the Malapert Massif is one of the areas that has been called out as a candidate Artemis 3 landing site. Going back decades, Paul Lohmann of Goddard identified that as a candidate place for exploration. So this is not new. Right? Some of these places we've known for decades are very interesting. I like Malapert Massif because not only is it a very high point from the summit of Malapert, you can look out, you can see the South Pole, and you also can see the Earth 100% of the time. And so there will be that nice connection that we'll be able to see. Some of the candidate regions, the Earth may be behind topography. You may not be able to see the Earth. So for me, Malapert becomes very interesting because it has this guaranteed line of sight to the Earth. It is also part of this high mountain associated with the South Pole Lake and Basin, a feature that we've talked about before. And so there's a direct connection to this ancient terrain and the possibility of collecting samples there that reflect the age of that basin, which I find to be very exciting. But each of the 13 has their own story. Natalie, any of the 13 stand out to you as places you would want to go?
I mean, they were all in SPA, so they were all in the South Pole. So any of them that has that impact melt from SPA would be hugely exciting for me. I agree. Anywhere that has the uplifted rim, and that would. So I don't have a favorite as it is now. All 13. I mean, I want to go all of them. Yeah. But yeah, I don't have an outstanding one as long as it brings back, as long as the mission brings back impact melt or that crazy complex material, regolith material. Every single site is going to have that type of material that is going to give us good information about that region, and it's nice and complex. So that's the kind of material I would want bringing back, and you can get that on all 13 of those places. So yeah.
I know we're running out of time, so I'll just say same. I mean, I think volatiles and PSRs tend to get a lot of attention. My heart is with South Pole Lake and Basin chronology and impact melt as well, actually. That's my academic background, and I just think it's just amazingly powerful to be able to do that, and I agree that I don't really have a favorite, but perhaps Dan might have a more interesting answer.
I'm going to weasel out as well. I think we have 13 great candidates. I think no matter where we go, it's going to be great. But one thing I do want to say that I'm really looking forward to is in April, NASA is hosting a lunar surface science workshop where they've solicited input from the wider lunar science community for folks to weigh in on what may be their favorite landing site of the 13, or what are some good ways to evaluate the full group of 13. So with that, I'll be talking about some of the compositional, the compositional considerations we're looking at. So where does mineralogy of the South Pole tell us that more South Pole Lake and impact melt might be? Yeah. I have to finish my analysis before then, so I don't have any answers right now.
2 weeks, all right.
We've got a few weeks.
I would say that an important thing to keep in mind, and I have a hard time remembering this. So yes, I was just announced as the project scientist for Artemis 3. Barbara Cohen, also of Goddard, will be the project scientist for Artemis 4. There will be an Artemis 5. There will be an Artemis 6. What we will learn from Artemis 3, I hope, informs some of the things in the places that we go from Artemis 4. Yes, the moon is in a vacuum, but the things that we do there are not done in a vacuum. That we will learn from Artemis 3, and my goal for that mission is that it puts us in a position where Artemis 4 can go gangbusters to a different location, confirm or refute some of the things that we find, and that it becomes this building block to subsequent missions that build on the legacy that we're laying the foundation for right now. So wherever we go, any of those 13 places have an opportunity to do that, to lay that foundation. It's really going to be up to all of us, not just the 4 of us up here, but everybody at Goddard and all scientists around the world, and actually all of the public, to get engaged with the mission, contribute to the mission, and then use the lessons from that mission to prepare for what's next. So I think with that, we'll go back to Bree and close out maybe.
So I'm going to run through 3 questions online in like a speed networking type way.
Got it.
So like in 30 seconds or less. So the first question is, and Dan, you kind of mentioned this earlier, that the moon gets bombarded by a lot of stuff. But so the Earth gets the meteorites from the moon, but does it go in reverse? And how can you tell the difference between what is moon and what is the reverse?
Sure.
That was asked for Dan, but
Yeah,
why don't you
Dan,
fight it out, you two?
Okay. Well, so I guess I'll take the part about how do you know it's from the Earth rather than from the moon. So you can imagine each planetary body, especially the moon and the Earth, has its own kind of fingerprint, as it were, based on its chemistry and how far away it's from the sun and what's happened. So, you know, we didn't realize, take for instance, Mars. We don't have physical samples brought back from Mars, but we actually know. Not yet. But we have Martian meteorites that we know are from Mars. And that's because we have orbiters going around Mars that we know are sending this chemistry data back, and we know that's Martian chemistry. It's different to Earth chemistry. And we know the same thing about, say, an Earth rock that may be on the surface of the moon, which I am a firm believer that there definitely is pieces of the Earth. Yeah.
There was a study a couple years ago that found potentially Earth sample in an Apollo 14 breccia.
That was, yeah.
And again, using those fingerprints, where again you look, we've gotten very good at identifying moon rock, not a moon rock. And you look at a moon rock and you say, well, that little piece isn't a moon rock. It's different. Maybe it has a little more water. Maybe it has a slightly different composition. And say, that looks like it could have formed on the Earth.
Yeah.
Unfortunately, there's no one around to say, oh yeah, I remember when that meteorite struck. I sent the rock there.
We need a time machine.
Absolutely.
Yeah.
But in that sense, also, we've talked a few times today about on the Earth, you have precipitation, you have plate tectonics, we have big oceans. Things are not preserved on the surface of the Earth for very long. But if you want a sample of the Earth from 4 billion years ago, maybe the moon is your best place to go get one.
Sure.
All right. And this one is specifically for Natalie. Have you found anything unexpected, unusual, or exciting in your recent lunar sample studies?
So, not unusual. I've not found any of those new minerals or anything like that yet. But we have had a really good project, which we do have a sticker for, because you know it's called Moon United, our team, for reasons of football, soccer, and the moon, my two loves. But we have a project working on Apollo 17 samples as part of the Apollo Next Generation sample analysis. And I guess the exciting thing about that whole project is like we're preparing for Artemis. We're using that to prepare for Artemis. So we're seeing how, how we would bring a new sample back and how all the wonderful teams across the world would analyze that sample. And we're not finding like unusual stuff, but we're finding new data about these samples, how old they are. Most recently, scientists have found that we have, and Dan touched on it a little bit before, we have volcanic samples that are 2 billion years old. And for the moon, for the last, we kind of assume it's, in a way, compared to the Earth, geologically dead. But no, we had volcanic eruptions that were 2 billion years ago. And how do you get that kind of heat source to create those volcanic eruptions on a planetary body that's kind of, quieter than what the Earth is? So that's kind of exciting. But right now we're working on the Apollo 17 samples, and hopefully we'll have some new exciting results in the next few months.
Absolutely.
All right. And so this is the last question. Anybody can answer it. It is believed that the moon is one plate, but is the team hoping to find evidence that could challenge that idea and discover that there are ancient plate boundaries that have been clustered together and became covered as the moon's mass decreased?
So there's a lot buried in that question, and goes to an assumption that we have since Apollo about plate tectonics on the moon and the structure of the moon, and we know that the history of the moon is complicated. Vishnu is in here. He's done a really detailed study looking at the early history of the moon and trying to reconstruct what happened. We have assumptions that we carry over that the moon is a one-plate object. We don't see evidence for large-scale plate tectonic features like we see all across the Earth, but that's a hypothesis worth testing, and the best way to answer that is through seismology. We can look at the moon. We have data from a spacecraft called Grail that painted a gravity and interior picture of the surface, interior of the moon. But when you fold into that modern seismology, what are the I guess it's not plate tectonics, but what's the tectonic activity on the moon? Kelsey talked about moonquakes, going and measuring where those moonquakes happen. Apollo did that from several locations all on the near side of the moon. If you have a global network, if you have seismometers scattered across the surface of the moon, you get a more accurate four-dimensional picture of the moon, of where those moonquakes are happening. And maybe you start seeing clusters. We know from the Apollo data that there are clusters of moonquakes that appear to form in specific locations. Could those be ancient plate tectonic boundaries, evidence for ancient plates? We don't know. We know that we need more data. Unfortunately, there is this rich history of bombardment on the lunar surface, gigantic impacts. The South Pole Aitken Basin being the largest, 2,500 kilometers in diameter. A lot of that ancient history does get erased. And so the prospect of going back to, well, what was the moon exactly like 4.2 billion years ago, might not be able to get there. But until we have all of the puzzle pieces laid out in front of us to start telling that story, we know that the story is incomplete. And that's why we have to go back.
Well, I want to thank you guys for being here. Thank the panel members, our audience in person and online. So that concludes our panel for today, but please stay tuned for the announcements for the Engage sessions in the future. Thank you.